In 1977, NASA launched two spacecraft the size of a small car, powered by a nuclear battery about as strong as a household generator, guided by computers weaker than a modern wristwatch. Those spacecraft, Voyager 1 and Voyager 2, are still out there, right now, still transmitting. Voyager 1 is over 15 billion miles from Earth, so far away that a radio signal traveling at the speed of light takes more than 22 hours to reach us. It crossed into interstellar space in 2012. A machine built in the 1970s is now drifting between stars and still talking to us. And almost nobody talks about this. Not because it isn't extraordinary, but because the things that are truly extraordinary about space get buried under rocket launches, billionaire vanity projects, and endless debates about the moon. The real story, what humanity has actually discovered about the universe in the last 50 years and what that means for our future and our understanding of reality, is almost never told in plain language. So here's what we're doing today. I'm going to show you 4 things modern astronomy has revealed that are so strange and so poorly communicated that most people have no idea they exist. I'll show you what Voyager 1 revealed about the edge of our solar system and why it was weirder than expected. I'll walk through what the James Webb Space Telescope is finding and why some of it is causing genuine tension in cosmology. I'll explain the Fermi Paradox not as a thought experiment, but as a mathematical problem with implications most people are not prepared to sit with. And I'll show you what we actually know about where the human species goes from here, what becoming multiplanetary realistically looks like, and why the gap between what's possible and what we're doing is one of the defining stories of our time. This isn't about inspiration, it's about scale, because most people are looking at a thumbnail of reality and thinking it's the whole picture. Imagine you've lived your entire life in a single room. You know every wall, every sound, every corner. Then one day, someone opens a door you never noticed, and behind it is not another room, but a hallway that stretches so far in both directions you can't see the end. Every door along that hallway opens onto something your room gave you no framework to understand. That's where modern astronomy has placed us. We opened the doors. What's behind them doesn't fit the room we came from, and instead of reckoning with that, we keep redecorating the room. Let me start with the edge of our solar system. For most of history, we thought the solar system was the sun, the planets, the moons, and asteroids, clean and bounded. We now know it extends vastly farther than the planets. Neptune orbits about 2.8 billion miles from the sun, but the Oort cloud, a huge shell of icy bodies still belonging to our solar system, may extend roughly 100,000 astronomical units from the sun. The solar system is not slightly bigger than we thought, it is orders of magnitude larger. But here's where Voyager 1 gets strange. In 2012, mission scientists saw something unexpected. The solar wind, high-energy particles streaming outward from the sun, suddenly dropped almost to zero. At the same time, cosmic rays from outside the solar system spiked sharply. The transition was much cleaner and more abrupt than scientists predicted. The boundary between our solar system and interstellar space, the heliopause, turned out to be sharper than scientists predicted, almost like a membrane. The sun's influence doesn't just slowly fade out, it ends. That matters. It means every star likely creates its own bubble of influence too. Interstellar space is not just empty background, it's a landscape of stellar bubbles and the strange regions between them. Voyager 1 is moving through a place humanity had never directly sampled before, and the data coming back is already showing magnetic field orientations and plasma densities that don't fully match our models. We sent a spacecraft beyond the solar system and immediately learned that our map of what lies beyond was incomplete. Now let's talk about the James Webb Space Telescope, because this is where things go from remarkable to unsettling. Webb launched in 2021 and began returning science images in 2022. The pictures are extraordinary. Deep fields full of galaxies, exoplanet atmospheres, stellar nurseries. But popular coverage mostly missed the part that matters most. Some of what Webb found doesn't fit the current model of how the early universe should have looked. The standard cosmological model predicts that in the first few 100 million years after the Big Bang, the universe should contain small, irregular early galaxies still in the process of forming. Large, mature galaxies shouldn't exist yet because there simply hasn't been enough time to build them. But Webb found massive galaxies, in some cases as massive as the Milky Way, appearing when the universe was only a few 100 million years old. Galaxies that look too old, too large, too developed for the amount of time available. Not a small discrepancy, a real one. Among researchers, the reaction was not just amazement, it was tension. Some of these galaxies appeared too mature for the age of the universe they're sitting in. It doesn't necessarily mean the Big Bang model is wrong, but it may mean that galaxy formation in the early universe happened faster or under conditions or through mechanisms that our current models don't capture well. And that pattern should feel familiar. Every time we build a better instrument, reality turns out to be more complicated than the old model suggested. Newton was powerful, then incomplete. Einstein was powerful, then incomplete. Every deeper layer reveals a more complicated structure underneath. Webb is opening a layer we've never seen before, and it already looks surprising. Now let's get to the Fermi Paradox. In 1950, Enrico Fermi asked a question that still has no satisfying answer. Where is everybody? The Milky Way contains between 100 billion and 400 billion stars. We now know most stars have planets. Many sun-like stars likely have planets in the habitable zone. That means tens of billions of potentially habitable planets in our galaxy alone. The galaxy is about 13 billion years old. Even if life is rare, simple arithmetic suggests that life should have arisen many times. And if even a small fraction of those planets produced technological civilizations, and if even some of those civilizations expanded at modest speeds, they could have spread across the galaxy in 10 to 50 million years. That sounds long until you compare it to 13 billion years. It's nothing. So where are the signals? Where are the artifacts? Where is even one unambiguous sign that another technological civilization has ever existed? After decades of searching, the answer is nothing. Silence. That silence is strange, and the explanations range from mildly unsettling to terrifying. Maybe we're early. Maybe technological civilizations are rare, and we happen to be among the first. Maybe the conditions for complex life are much rarer than they seem. Maybe there are civilizations out there, but we're searching the wrong way. We've mostly looked for radio. Advanced civilizations might communicate through methods we haven't learned to detect. And then there's the explanation that deserves the most attention: the Great Filter. The Great Filter idea says that somewhere between simple chemistry and galaxy-spanning civilization, there is a step so improbable or so lethal that almost nothing gets through. And the terrifying part is this: the filter is either behind us or ahead of us. If it's behind us, then some step in our past, the origin of life, complex cells, intelligence, language, was astonishingly rare. That would be cosmic good news. We already passed the hard part. If it's ahead of us, then civilizations usually reach our level and then destroy themselves. Nuclear war, engineered pandemics, AI, climate collapse, some technology that repeatedly kills the species that invents it. If the filter is ahead, then the silence of the galaxy is not just mystery, it is warning. The honest answer is that we don't know, but the mathematically honest answer is that the silence requires explanation. Space is huge, yes, but 13 billion years is also a very long time. Silence is not nothing, it is data. Now bring Not back to us. NASA's roadmap still centers on returning humans to the moon through Artemis and eventually using that as a stepping stone to Mars. SpaceX is building Starship with similar long-term goals. Other space agencies are also developing deep space capability. Human spaceflight is more active now than at any point since Apollo. But here's the honest version without the public relations layer. Mars is hard. Not a little harder than the moon. Categorically harder. The moon is 3 days away. Mars is a 2 to 3 year round trip. During that time, astronauts face deep space radiation with no Earth magnetic field protecting them. There is no quick rescue. Mars itself has almost no atmospheric protection, no global magnetic field, toxic soil chemistry, brutal cold, and no easy access to liquid surface water. Everything needed for a human settlement, air, water, food, radiation shielding, energy, manufacturing, has to be brought, built, or both. It can be done, but it is much harder than the optimistic version sounds. And still, we should be doing it faster. Because if the Great Filter is ahead of us, then a single planet civilization is a civilization with a single point of failure. Every existential risk, asteroid impact, pandemic, climate cascade, war, technological accident, some technology that repeatedly kills the species that invents it. If the filter is ahead, then the silence of the galaxy is not just mystery, it is warning. The honest answer is that we don't know, but the mathematically honest answer is that the silence requires explanation. Space is huge, yes, but 13 billion years is also a very long time. Silence is not nothing. It is data. The same is true of becoming multiplanetary. The technical path exists. The investment does not match the stakes. Global spending on space exploration is tiny compared with what we spend on trivial things. That isn't a moral attack on those things. It's an observation about priorities. And if the Fermi Paradox is telling us something real about how hard survival is for technological civilizations, then the silence of the cosmos may be the most important data point our species has ever encountered. The rational response would be a serious, well-funded effort to ensure long-term human continuity beyond one fragile world. That is not happening at the scale it should. But I don't want to leave you only with fear. The same species that built Voyager 1 in the 1970s and still hears from it across 15 billion miles also detected gravitational waves in 2015, ripples in space-time from black holes colliding a billion light-years away. That same species took an image of a black hole by linking observatories across the planet. That same species landed a helicopter on Mars and flew it in an atmosphere barely thick enough to support flight. The capability is real. The curiosity is real. The question is whether we are pointing enough of that capability at the right problems fast enough. The observable universe is about 93 billion light-years across. It contains an estimated 200 sextillion stars. Against that backdrop, every war, every border dispute, every human struggle over resources or ideology happens on one pale dot orbiting one ordinary star in one galaxy among hundreds of billions. That perspective is not meant to diminish life on Earth. It is meant to expand the frame, because the species that can understand that perspective and still choose to build the tools and institutions needed to move beyond this single fragile world is a species worth preserving. The edge of everything we know is not a wall, it is a door. Voyager 1 already went through it. The question is when the rest of us follow and whether we do it deliberately enough and soon enough to matter. The silence of the cosmos is not background noise. It is one of the central unsolved problems in our understanding of intelligent life. And the two most plausible explanations, that we are rare or that survival is hard, both have profound implications for how seriously we should treat the future of our species. One of them should terrify us. Both of them should motivate us. What Webb is finding suggests our cosmological models are incomplete in ways that matter. We are not at the end of understanding. We are at the beginning of another layer of questions. The right response is not anxiety. It is better tools, better science, and serious investment. And the gap between what we are technically capable of and what we are actually doing about long-term human survival may be the most important resource allocation problem of our time. We have the knowledge, we have some of the technology, we have the map, we are under-investing in the expedition. The universe is not waiting for us to be ready. The math does not care about our timelines. The only thing that changes the outcome is what we decide to do next.